All right, I think we can get started. How's everyone doing today?
I'm good. I'm good.
I'm also good.
Good.
Cool. Well, glad you all are doing good. So today we're going to talk more about combinations. So some of it will be just applying what we learned last week, and then we'll look at kind of some more complicated problems to see all the sorts of types of problems we can solve using combinations, as well as some permutations. And then my plan is next week, we will start looking at probabilities. So basically, let's look at how basically combinations can help us solve problems where the question isn't obviously a combination. So let's look at this example, which is a problem that has at least two kind of reasonable ways to solve it. So the question is, how many games are played in a round-robin bowling tournament consisting of 12 players? And kind of as an explanation, in a round-robin tournament, each player plays every other player exactly once. So there's actually like a couple ways we could do this. And before we explain the combinatorial solution, or the one we use combinations to solve, we can kind of use casework to solve this problem. And we can even try to write down all the cases. And so here, I won't write down all of them. They've already been written down here. Please verify that this makes sense. But basically, we can just label the players 1 through 12. And then we can try to find the number of ways to pick two players by kind of organizing all the different possibilities. One way to kind of make sure we're not overcounting is we can always list the player with the smaller number first. So for example, first we list out all the players that player 1 is playing. So player 1 will play 1, I'm looking at the column here, 2, 3, 4, all the way to 12. So there's 11 here. And then we look at player 2. Player 2, we already counted player 1 here. So player 2 can play player 3 all the way through player 12. So there's 10 and so on. Excuse me. And so if we look at this whole list of different pairs of players, we can see that there's 11 plus 10 plus 9 plus 8 plus 7, 6, 5, 4, 3, 2, 1. And we can basically sum up all of these to get the total number. And then do you all remember from the first, I think it's the first lecture, how to sum these up?
Yeah, there was a formula for it.
Yeah, so basically when you have a sequence like this, 1, 2, 3, all the way to say n, the way we sum it up is we can pair these numbers together. So for example, we can pair 11 with 1, 2 with 10, and that gives us 11. Sorry, that gives us 12, right? And then how many pairs are there? There's sort of the total number of numbers divided by 2. So in this case, the sum here equals 12 times 11 divided by 2, which equals 66. Any questions on that solution? We're going to explore a different way of doing it if there's no questions on this one. All right. So this solution is pretty organized, but let's take a look at another way we could do this, leveraging what we learned about combinations last week. So we could think of each game in the round robin tournament as a committee of 2 players, or for example, like that we want to choose the number of, choose 2 players out of a pool of 12 players. And so the question, we can transform it into how many ways are there to choose a committee of 2 players out of a whole group of 12 players. And so then we see that the answer would be 12, choose 2. And then if we calculate out 12, choose 2, of course, it ends up being the same as our previous answer, which is 16. So does everyone see why this is an equivalent solution? Or does people have any questions about this explanation? And so if we do it this way, we don't actually have to write down all the cases. No questions?
No, please.
All right, cool. So I think the takeaway here is we need to sometimes transform a problem into thinking about something in terms of combinations and permutations, even if the problem isn't explicitly like how many ways are there to choose 2 players. But by kind of understanding the problem first, we can see that that could be transformed into just thinking about how do we count the number of combinations of 2 out of 12. So we'll do a lot more examples of this today. So hopefully by the end of the lecture, we're starting to develop more of an intuition about when we can use these techniques. So let's look at another one, and I have a little bit more space here. So one thing to note before we get into the problem is if we want to choose k things out of n things, that's n choose k. And one way to kind of transform this choose a committee of k people from a group of n people problem is this is equivalent to saying, how do I choose k element subsets? So a subset that has size k out of a set of n elements. And those are both equivalent to n choose k. So basically, once we see that, we can use this relationship to help us solve counting problems that relate to counting subsets. Does everyone understand that? So basically, if I have say a set that has n elements in it, let's say it could be as simple as like I have the set and then I want to say how many subsets of S have k elements, then that's going to be is n choose k. So let's do an example with this. It's okay if that didn't fully make sense, and we'll see from here. So instead of using n and k, let's consider a set with 5 distinct elements. You can imagine it's like 5 numbers that are different, or 5 marbles that are different, whatever. How many 0 element subsets are there? And just feel free to speak up. Yep. Can you give a short explanation?
Yeah, so it would, if we're looking for 0 element subsets, it would be choosing 0 out of 5 to form a subset, and 0 factorial is the same as 1. So at the end of it, you'd still have 1.
Yeah, so basically you can kind of intuitively think there's only one 0 element subset, which is the empty set. And then you can also think, okay, if I want to choose 5 from 0, that's like 5 choose 0, which is 1. All right, what about B? How many 1 element subsets are there?
5.
Yep, 5. So we have 5 elements. Each of them could be in this 1 element subset. So we can imagine, let's say S equals 2, 3, 4, 5. Then these 5 subsets are 1, 2, 3, 4, 5, right? All right, so now let's go a little bit more complicated. How many 2 element subsets are there?
10.
And can you explain?
In this case, you are doing 5 choose 2. So it will be 5 factorial divided by 2 factorial, 3 factorial, which will give you 10.
Okay. What about 3-element subsets?
10.
Yeah, it's 10 again. Same reasoning. What about the next one?
5.
Yep. And then lastly, how many 5-element subsets are there?
1.
Yep. All right. So now let's explore this kind of cool property. So let's add up all our answers from the above. What do you get?
32.
Yeah, you get 32. And this is interesting because it's actually, we could notice that 32 is 2 to the 5th power. And so one interesting thing is if we think about another way to count all of the subsets of a 5-element set, we can think, okay, so if we're summing up all the 0-element subsets, all the 1-element subsets, all the way to all the 5-element subsets, what we're really counting is how many subsets exist of a set of 5 distinct elements. And so going back to what we learned in previous weeks, how do we count the total number of subsets of a 5-element set?
You sum the amount of the results of finding each of the different possible subsets, 5, 2, 0, and then you sum.
Yeah, so
Well,
that's what we just did above.
You could
Sorry.
also do 2 raised to the power, the number of elements in that set, because that's what we are taught at school.
Yep. Yeah, so this is what we've discovered here is that if we want to count all the subsets of a 5-element set, we can basically say, so I'll say number of subsets of 5-element set. This is 2 to the 5th. Does everyone know if we count it that way, why? Or whoever said that, can you give a quick explanation? Why is it 2 to the 5th?
Because the number of elements are distinct.
Yes, they're distinct. But the 2 to the 5th comes from, okay, so I'll just explain the way I think about it. The 2 to the 5th comes from the fact that for each element, you have 2 choices. One is to not put it in the set, and one is to put it in the set. And so if we think about how many ways are there to choose, whether to put all these 5 elements in the set or not in the set, then we get 2 times 2 times 2 times 2 times 2, because for each element we have those 2 choices. The other way we can count the number of subsets of a 5-element set is by saying, okay, let's actually count all the different size subsets, and this is basically using casework. And so from there, we see that equals 5 choose 0 plus 5 choose 1 plus 5 choose 2 plus 5 choose 3.
Wait, but how exactly do you get 1 from 5 choose 0?
Great question. So 5 choose 0 is basically 5 factorial over, okay, so remember that n choose k equals n factorial over n minus k factorial times k factorial. So basically, if we plug in 5 and 0, then we get 5 choose 0 equals 5 factorial over 5 factorial times 0 factorial. We define 0 factorial as 1. And so this equals 1. So this is kind of special. Basically, it's nice if we can refer to 0 factorial as 1. So going back here, we've kind of found this interesting identity for 5. So 2 to the 5th equals 5 choose 0 plus 5 choose 1 plus 5 choose 2 all the way to 5 choose 5. And so we can even generalize this. So let's say we want to count the number of subsets of an n element set. We can basically think about counting it 2 different ways. The first way is what we did above, which is we count how many 0 element subsets, how many 1 element subsets, how many 2 element subsets, all the way to n, and we sum those up. So if we count it that way, then we have n choose 0 plus n choose 1 plus n choose 2, all the way to n choose n minus 1, n choose n. Does everyone see why that's the case? We're just kind of generalizing what we did above.
Yeah.
Any questions? Okay. And then if we count the same thing, number of subsets of an element set, in a different way, by just counting kind of directly, we have n elements, and for each subset, we can choose for that n element, whether it's in the set or not. So we have 2 choices. Then that equals 2 to the n. So now we've kind of proven or derived this interesting identity, which is that if you sum up all of the combinations of n from 0 to n, that equals 2 to the n. Any questions on this? All right, if not, let's look at some examples of problems that we can do with what we just learned about counting subsets. So this is a kind of different question, but it's still a counting question. So the question is, find the maximum number of points of intersection between 12 lines in a plane. So for example, we can say, okay, if there's 2 lines, the maximum happens when we just have 2 lines that intersect. So there's 1 crossing. If we have 3 lines, maybe the maximum is something, you have a configuration like this. You have 3 lines, 3 intersections. If we have 4 lines, maybe we can try drawing something like 2, 3, 4. Then we have 1, 2, 3, 4, 5, 6. So anyone have any ideas on how we can do this for 12 lines besides drawing out 12 lines?
We can try and sum the total combinations. So we can start with choosing 2 lines to intersect. So 12 choose 2 plus 12 choose 3, and then so on and so forth.
So you said we could start by choosing 2 lines to intersect. That's 12 choose 2. What does the 12 choose 3 count?
So afterwards, you'd make it 12 choose 3 because of the fact that now we are choosing 3 of the 12 lines to intersect with each other. So, and then you'd sum the total point of intersection after you intersect all the lines.
I see. So you're close. So if we think about what an intersection is essentially when 2 lines intersect. So we'll have the maximum number of points of intersection if we always have 2 lines intersect at one point and no more than 2 lines. So for example, let me just do a different example here. So if there's 3 lines and they all intersect at one point, then that's not going to give us the maximum number. Then this will only have 1 point of intersection. And so we get the maximum when every line intersects every other line once. And so you're close when you said we need to do 12 choose 2. Basically, if we do 12 choose 2, then we'll get the number of pairs of lines. And then we know that for every pair of lines, we have 1 point of intersection. So actually 12 choose 2 will just give you the maximum number of points of intersection. If you start adding 12 choose 3, it's actually going to be overcounting because we don't need to count like sets of 3 lines. We only need to count sets of 2 lines. So in this case, we actually just want to do 12 choose 2, and that's 12 times 11 over 2, which is 66. Any questions on this?
So when we're choosing 2, are we saying that we're pairing the lines so that each of them at least crosses once? So if you were to actually take 12 lines and make it so that they each intersect once, this is the number of points?
Yes, that's right. So basically, if we had lines that didn't intersect, then we would not have the maximum number of points of intersection. So for example, other ways that we could have not the maximum. So here we have the maximum. And then here's sort of like a non-maximal way. Another way that would be not maximal is if you had 2 parallel lines and a third line, then you would only have 2 points of intersection if there were 3 lines. Similarly, if there are 2 lines, you can either have 1 point or you have 0 points if they're parallel.
Okay, thank you.
So if we want maximum, we have to basically have all of them intersect all of the other ones. All right, so let's look at problem B, which is very similar. So it says find the maximum number of points of intersection between 12 lines, given at least one of them, the pair is parallel. Any ideas on this one?
If one of the pairs are parallel, it means that they won't intersect. So you just have to do 66 minus 1, which will give you 65.
Yep. Does everyone see why that's the case?
Yes, please.
Yeah. So basically, yeah, what was said was correct. Basically, if we want the maximum, then we basically say only one pair is parallel. That means out of all the 12 choose 2 combinations of pairs of lines, one of them will intersect, but all of the other pairs will intersect. So we just subtract 1. Cool. All right, let's try a couple more and then, go ahead.
So a general formula for that be, if it's n, it will be n times n minus 1 divided by 2.
Yep. So if we want to look at the maximum number of points of intersection between n lines, we can basically generalize that. So we want to say, okay, how many pairs of lines can we choose from these n lines? And then all of them would need to intersect. So we could just do n choose 2, which, as you said, was n times n minus 1 over 2. Yeah, that's right. So we can also verify for these few examples that I drew. So for example, if there's 2 lines, then we have 2 choose 2, which is 1. If there's 3 lines, then we have 3 choose 2, which is 3. If there's 4 lines, we have 4 choose 2, which is 6. All right. All right, we'll do a couple other kind of examples of these like subset counting, and then we'll move on to a different type of problem. So here's another question. It's framed in a different way. Basically, find the number of 4-digit natural numbers whose digits are in ascending order. So how can we transform this into a counting problem where we use combinations?
We could start by finding the total amount of 4-digit numbers.
Okay. How does that help us?
When we have the total amount, we can try and find a pattern within that total amount so that we can say something like maybe in every 10 numbers, the numbers that are in ascending order are this. So we could start by saying choosing out, we could say n numbers, the total numbers of 4-digit numbers, and the total number of patterns that occur, reoccurrences of ascending numbers.
Could I just say something? I don't
Yeah.
think that would be 100% correct, because as you move on and go higher, the number you get will reduce.
Yeah, I think I see what both of you are saying. So you could try to get the answer by sort of casework. So if you remember the first problem we did today, there's often multiple ways you could do something. And so one way you could do this is, let's like carefully count how many numbers there are. We could start like listing them out and then counting very or in an organized way, and then sum all of them together. I also see the comment about like they're not going to be evenly spaced. So for example, you're going to have more numbers that start with 1 that are in ascending order than numbers that start with 6 and are in ascending order. So is there another way we can count this by avoiding having to do sort of casework and listing them out? I'll give a hint. This is related to finding a subset of number of subsets of some set. All right, so say we have 4 natural numbers. So let's not include 0 for now. And let's say I have like 1, 3, 7, 8. For any set of distinct sort of digits, I'll say, rather than numbers, really we care about the digits. We see that there's only one way to create a 4-digit natural number whose digits are in ascending order. Basically, if I have these 4 digits, the only way I can make a number that satisfies this property is by putting them in one order. All of the other orders will not give me ascending order. So with this hint, any ideas? So let me explain how we could do this one. So basically we could look at what are the possible sets of digits, because we can note that for every set of 4 digits, that maps to one natural number that satisfies this property. So for example, for the set 1, 3, 7, 8, there's one number that it can form whose digits are in ascending order. And we also note that we can't have 0 in the set, because if we have 0 in the set, then we end up with something like 0, 3, 7, 8, which is actually just 378, which is not 4 digits. And so we can reduce this problem to, I'm going to just write it out. How many ways can we choose a 4-element subset of 1, 2, 3?
I'm sorry to interrupt, but I kind of got disconnected for a while. Do you think you could start over?
Sure. So basically, the thing to note here is that if we have a set of 4 digits, for every set of 4 digits where the numbers are distinct, that will lead to basically one 4-digit number whose digits are in ascending order. So for example, in the set 1, 3, 7, 8, that leads to the number 1, 3, 7, 8, which is 4 digits and in ascending order. We also note that we can't use 0, because if we have 0 in our subset, then that will lead to a 3-digit number. So basically I've transformed this problem statement into a different one, which is how many ways can we choose a 4-element subset of the set 1, 2, 3, 4, 5, 6, 7, 8, 9. Does everyone see why these are equivalent problems, or does anyone have any questions about this reasoning? Because once you see this, then this has been reduced to a problem we already know how to solve. Okay, no questions. So how many ways can we choose a 4-element subset of 1, 2, 3, 4, 5, 6, 7, 8, 9? Anyone remember that?
Could it be 9 choose 4?
Yeah, so it's just 9 choose 4 here. Basically, this is the same as now the problem that we covered earlier. So basically, if we have a set of 9 elements and we want to choose 4 elements from it, that's just 9 choose 4. And so if we do 9 choose 4 and we want to expand this out, this is 9 times 8 times 7 times 6 over 4 times 3 times 2 times 1. And then I believe this turns out to be something like 126. We can cancel this out. Times 2. Yeah. Any questions about this? I know this one's a little bit trickier.
So all we have to do is just break the question into a more familiar form to try and solve the answer.
Yeah. So here the insight we need to make is just that for every subset that has 4 elements, that will create a 4-digit number where the digits are in ascending order. Yeah. So we'll do more examples to kind of build this muscle. And I'll try to do like a variety of different ones, right? So here's another one. So we'll see if we can derive the formula for the number of diagonals of a regular n-gon, where n is greater than or equal to 3. And so a diagonal, just to make sure we're on the same page with that, is a segment that directly connects two vertices of a polygon that are not adjacent. So for example, let's go through some examples. So if n equals 3, then a regular n-gon is a triangle. It's an equilateral triangle. And we actually don't have any diagonals. Number of diagonals. Let's do this. Because all the vertices are adjacent. And so there's no line segments that we can draw that connects two vertices that are not adjacent. Now let's look at when n equals 4, then a regular 4-gon is a square. How many diagonals does a square have?
4. 2.
Yeah, so there's 2. Let me use a different color. Maybe orange or something. So there's 2 diagonals, just like here. All right, we'll do a couple more examples and then we'll derive the formula. But I just want to make sure everyone understands the concept of diagonal. So for 5, we have a regular pentagon. How many diagonals are here?
5.
3. No. What's wrong with me?
So let me just
6.
draw them out. It's the easiest way to count it right now. So there's 5, right? Am I missing any? All right, 5. You can do a couple more. So for 6, it's going to be a regular hexagon. Sorry for this. Okay. And then again, we can draw them out. So maybe I draw it like this. 4, 5, 6, 7, 8. If there's 7.
There's a nice one.
Sorry? Oh, I missed one, yes. It's like, it looks a little weird. Here we go, right?
Yeah.
Thanks. Okay, so that's my attempt at drawing a 7 gone. And then here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. All right, so we've done a couple examples. Anyone have any questions about what the problem is saying or what we're trying to count? All right, so now let's see how we can actually derive the formula for number of diagonals by using counting and combinations to count this. So if we think about diagonal as a segment that directly connects two vertices of a polygon that are not adjacent, we could count this by saying number of diagonals. There's a couple ways we can count this, but let's try first use combinations. So number of diagonals equals number of segments that connect two vertices minus number of segments that connect two adjacent vertices. So here I'm just taking this definition up here basically we want segments that connect two vertices that are not adjacent. So the way we could count that is we could use complementary counting to find the number of segments that connect two vertices and then subtract out the number of segments that connect two vertices that are adjacent. So if we want to count the number of segments that connect two vertices, how many ways are there to do that using combinations?
N minus N choose 2.
Right, so this is just n choose 2 because we have n vertices. I didn't define, but a vertex is basically a point of the polygon. So all of these are vertices. So we have n of them. If we picked any two of them, that will create a line segment that connects them. And then how many segments of that connect two vertices will connect two adjacent vertices?
0.
Why is that?
Is it n?
Because two adjacent vertices are already connected by the sides.
Right, so there's actually n of them that are there's n sides for an n-gon. And so there are two segments that connect, there's n segments that connect two adjacent vertices. So in my drawing, I'm not counting them for the diagonals, but when we count the number of segments that connect any two vertices, we are counting them. So if we say n choose 2, we're counting every pair. For example, we're counting this and this, we're counting this and this, this and this, and this, and all of the pairs. So we are including the sides in that count. So we need to subtract out the number of segments that connect two vertices, which is n. So if we expand this out, what we get is n choose 2 is n times n minus 1 over 2 minus n. And then we can sort of combine this together. So this will actually give us, I guess we could do this in many ways, but let's say we just expand it out, n squared minus n over 2 minus n, which is squared minus n minus 2n over 2, n squared minus 3n over 2, which is n times n minus 3 over 2. So this is the formula for the number of diagonals of a n-gon. And we use combinations to solve it. Any questions?
No, please.
So I'll just really quickly talk about another way we could derive this formula that's also using counting. So basically another way we could think about this is for every diagonal, we can first pick an endpoint. So there's n vertices. That could be one endpoint. And then for the other endpoint, how many choices are there? And so we see that there's n minus 1 other vertices that could be chosen, but there's 2 of those are adjacent. So we actually don't want to choose an adjacent vertex. So there's n minus 1 total other vertices, and then we want to subtract out the 2 that are next to it, which gives us n minus 3. And then the last thing we need to do is correct for overcounting, because here, if we pick sort of this point first, if we pick, say, this point first and this point second, that's going to be the same diagonal as picking this one first and the other one second. So last thing we need to do here is divide by 2 to correct for overcounting, and this gives us n times n minus 3 over 2. So that's another way you can think about it. But I think the first way is a little bit more clear and more directly related to the subset combinations. All right. So now let's look at a different class of problems also related to combinations. So here we're going to look at what we call path walking exercises. So again, we'll do an explanation with an example. So consider this problem when we want to count the number of paths of something. So here we're saying in order to get home, Kelly must travel 3 blocks to the south and 2 blocks to the west, and she can move 1 block north, east, west, or south at the corner of each block. How many possible paths could Kelly take to get home if she travels the shortest possible distance and she can't like cut through blocks by going diagonally? So let me just draw out what this looks like. So Kelly needs to go, let's say Kelly is here. Okay, let's say Kelly starts here. And it says to get home, she must travel 3 blocks to the south and 2 blocks to the west. So let's draw this. And kind of the grid keeps going, but. So this way is west, this way is south. And so if Kelly has to travel 3 blocks south and 2 blocks west, then her home is right here. Did I draw that out right? Any questions about that? All right, so now we want to count the number of ways Kelly can go from this point to this point. And then the other thing, and at every corner, she can go in one of 4 directions. So she can go north, east, south, or west. But let's note here that the question wants to ask the shortest possible distance. And so if we think about it, the shortest possible distance for Kelly to go has to be 5. And if she wants to only go 5, she can only go south and west. She can never go north because that will kind of go backwards, and she can never go east because for every time she goes north or east, she has to go an extra block down or an extra block to the right. And so here we can actually list the possible paths in alphabetical order if we want, which basically corresponds to ways Kelly could get home. So we could go through some examples. So here, if we do south, 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 west, west, the path that looks like is Kelly's going to go south, 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 west, west. That's one way. The next one is if she goes south, 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 southwest, southwest. So that would be south, oops, south, southwest, southwest. That's another path. South, southwest, west, south would be south, south, west, west, south. So we're just kind of methodically listing them out and so on. Does everyone see how each of these corresponds to one path here?
Yes, please.
Yeah.
And then does everyone see why if the shortest possible distance is 5, then it can only be 3 souths and 2 wests? We can't have any norths, we can't have any easts, and we can't have any other combination of souths and wests. Yeah?
Yeah.
Yeah.
Cool. So if we list out all the paths, we see there's actually 10 of them. And so that's one way we could get the answer is we could list them out. But now that we've listed out all the possible paths, we see that this is actually the same as a different problem that we solved before. Last week, if you all remember, we did a type of problem that was like, if I have 3 S's and 2 W's, how many words can I make from that? And so the way that we solved that was we did 5 factorial, and then we divided by 3 factorial times 2 factorial to correct for overcounting. So that gives us 5 times 4 over 2, which gives us 10. Another way we could solve this is we have 5 basically directions that Kelly needs to go, and we need to choose 2 of these blocks to move in the west direction. So say I pick, this one and this one, then the rest becomes south. So if we want to choose 2 of the 5 for Kelly to move west, and the rest will move south. Another way to write that is 5 choose 2, which is, again, 5 times 4 over 2, which is 10. And so if we think about it in the second way of choosing 2 out of 5, that's basically what we were learning earlier about forming committees. Basically, as I mentioned, we would want to pick 2 of the 5 blocks to move in the west direction, and the rest are south. And so that also another way to give us 10. So what we want to illustrate with this problem is another class of problems that we can solve with sort of these combinations and committee forming techniques is actually path walking. So if we want to count the number of paths to get somewhere, we can think about it as how many ways are there for me to choose basically the blocks of going in one direction. Any questions on that? We can go through some examples.
So I just want clarification of something. You found the minimum number of blocks, and then with that information, you then realize that if you choose the certain number of S's or W's, you can get your answer as to the number of paths available to it.
Sorry, can you repeat the question? I'm not sure I understand what you're asking.
I just wanted to find out how we really worked it out. I was wondering if it was based on the fact that 5 is the minimum number of blocks, so we're just going to assume that she's only taking the 5 block path, and we're just using south and west. And since there's 2 wests, we just do choose 2, but we can also do choose 3 for the 3 S's, which is the same as choose 2.
Yeah, that's right. That's correct. Basically, there are a couple parts to this problem, but it is important that it's the shortest possible distance, because if that wasn't the case, Kelly could take a path that's like, oh, okay, let me go down and right and up and left and down and side. Like that would be a different path, but it would not be the shortest. And so if we need to find the shortest one, then Kelly can only go 5 blocks, and out of those 5 blocks, 2 of them have to be west and 3 of them have to be south. So yeah, that's important. And then you're right, we could count it by saying let's choose 2 blocks out of the 5 for Kelly to go west, or we can say let's choose 3 of the blocks for Kelly to go south, and those will give the same answer. And remember last week we also talked about this identity where n choose k equals n choose n minus k. So here, that's what gives us that 5 choose 2 equals 5 choose 3.
Okay, thank you.
Yeah. All right, let's do a couple examples to make sure we get this concept. So here's another such example. So Amanda is standing at the origin and wants to get to the point 6, 4. And when standing at a point, she can either go to, so say she stands at point M, N, she can go to point M plus 1, N, or to point M, N plus 1. So let me draw this out and we can go from there. Try my best to draw here. Okay, so let's say this is the origin. The origin is 0, 0. And then she wants to get to the point 6, 4. So 1, 2, 3, 4, 5, 6. This is 6. So she wants to get here. Is that clear to everyone? All right. And then the second part is saying when she's standing at a point M, N, so let's say she's standing here, which is 2, 3. She can either go to point M plus 1, N, which means she's moving to the right, or she can go to the point M, N plus 1, which means she's moving up. So if she goes right, that will take her to 3, 3. If she moves up, that takes us to 2, 4. So now this is a path counting problem where basically Amanda needs to get from this point, the origin, to this point. She can only go up and right, and we want to count the total number of ways she can take a path there. So for example, this would be a path. So given what we just learned, anyone have ideas on the first part of the problem, which is how many possible paths could she take?
Well, like we did in the last question, we can find the minimum blocks needed for it to move, or the minimum movements she needs to make. So she's at MN, and we can say that from MN, if she moves this many times up or this many times to the right, and we sum it together, the total amount of times.
Okay, so what's the shortest, or how many moves does she need to take?
6 to the right and 4 up.
Right, so she needs to take 6 to the right and 4 up. Everyone see why that's the case?
Yeah.
And then
So,
we just do 10 factorial divided by 6 factorial.
right, so the answer to part A is basically we do 6 plus 4, choose 4. So basically, if we want to count the number of paths that have 6 rights and 4 ups, then basically we want to count the number of sequences that look like, say, R, U, R, U. That's, for example, 1. And so basically there's 10 blocks, and we need to choose 4 of them to be ups, or there's 10 blocks and we need to choose 6 of them to be rights. So this is 10, choose 4, which is and this is 210. Any questions? All right, let's take a look at part B. So it says how many of those paths travel through the point 4, 1. So 4, 1 is over here. So we want to count how many paths can Amanda take that go through this point. So for example, something like this would go through that point. So how might we do this one? Any ideas?
We can start by looking at the number of movements from origin to 4,1, and then the number of movements from 4,1 to the 6,4, the minimum that would take. So from origin, it would take 4 to the right, 1 up, so 5 in total movements, and then from 4,1,1 to 6,4, it's 2 to the right and 3 up.
Right. So if we want to look at number of paths from 0, 0 to 4, 1, that basically means 4 rights and 1 up. So this equals 5 choose 1, which is 5. For this one, it's basically 2 to the right and 3 up. So this is 5 choose 2, which is 10. And how do we combine these to get the total number of paths that travel through this point?
You multiply them against each other and it gives you 50.
Right, so we want to multiply them together. Does everyone see why we want to multiply them? Yeah, so just quickly, we want to multiply them because for any, this is like the, this is the rule of multiplication that we learned in the first week. So basically we can take any path that goes from 0 to 4, 0, 0 to 4, 1, any path that goes from 4, 1 to 6, 4, and that put together will give us the number of give us a path that goes from 0, 0 to 6, 4 through 4, 1. So if we multiply them, then we get all the different combinations of paths from here to here and paths from here to here.
I have a question.
Yeah.
Why is it that, like in choose, why is it that the bottom one has to be the ladder thing? Like for example, it's 5 choose 1. Why can't it be 5 choose 4?
Both
Or
of them give the same value.
Sorry?
Both of them give the same value.
Oh, okay. Okay.
Yeah, that's right. You can do 5 choose 4. And for the bottom one, you can do 5 choose 3. It'll give you the same one. So I kind of did a little shortcut here, but if you do 5 choose 1, right, that's 5 factorial over 4 factorial times 1 factorial. So that's actually the same as 5 choose 4. And then same for the one below. 5 choose 2 is 5 factorial over 3 factorial times 2 factorial. And that's the same as 5 choose 3.
Okay, yeah.
Cool. All right, so I'll walk us through another example. How many of you have heard of Pascal's triangle?
Yeah, I've heard of it.
Me.
Okay, cool.
I haven't heard of that.
Okay, that's okay. I'll explain what it is. But basically, Pascal's triangle, we can build it in this way. So we start with this triangle of 1, 1, 1. And the process we want to use is each term in the triangle is going to be the sum of the 2 terms immediately above it. And then we always have 1s on either side. So for example, for this next row, we'll start with a 1. And then for this element, we're going to sum these 2, and that'll give us 2. And then we have a 1 on the edge. For the next row, we'll start with 1. for this one, we're going to sum these two and we get 3. Sum these two, get 3, 1. Actually, let me draw this on the side so you have more room later. So 1, 1, 1, 1, 2, 1, 1, 3, 3, 1. What would be the next row?
1, 4, 6, 4, 1.
Right. And then what about the row after that?
1,
1,
5,
5, 10, 10,
1,
5,
5,
1.
10, 5, 1.
10.
Right. And so on. So this is Pascal's triangle. Any questions about how we are kind of defining it?
Harder?
Sorry?
I couldn't hear you. What you said.
Oh, I just asked if people have any questions on how we're defining it. Okay, cool. So let's start labeling some of these numbers and rows. So let row n be the row which is n rows below the initial entry of 1. So for example, let's call this the 0th row. This one can be row 1, row 2, row 3, row 4, row 5. And then we call the terms, let's call this like the 0th term, first term, second term, third term, fourth term, fifth term. And so for row n, we have n minus 1 terms. Or sorry, n plus 1 terms. Everyone see why that's the case?
Yeah.
Yeah.
So what we want to find in this problem is we want to look for an expression for the kth term on row n of Pascal's triangle. And let's see if we can use pathfinding to count this. So if we try to turn this into like a pathfinding problem, one way we could think about this is, let me just draw out a grid here. So let's say we want to get from point A to point, let's call this B. And we want to count how many ways there are to go from A to B. And let's say we can only move east and south. So we don't want to like, go in circles or go backwards. And so we saw earlier one way to count it. But another way we could count it is we could just sort of like carefully count how many ways are there to get to each point. And see if we can get to B. So let's try that. So how many ways are there to get, let me pick a different color, get from A to this point? If we can only move this way and this way. It's kind of an easy question. There's just one, right? Because I can only just go from here to here. Similarly, how many ways are there to get here? Just one. How many ways are there to get to this point from A? So if we could just chime in.
2.
Yeah, 2. And the reason that's 2 is there's one way to go from this point, which is just to move down, and there's one way to go from this point, which is just to move right. And then we sum those up, that gives us 2. All right, now let's kind of do the next part. So how many ways are there to get to here?
2.
Why is that?
3, because You can move from the 1 to that point and from the 2 to that point.
So you actually can't move from the 2
There's
to
only
this point
one.
because you can only move right or
There's only
down.
one.
Yeah,
There's
so there's
only
only one. And similarly here, there's only one. Because we can, remember, we can only move right or we can only move or down. So from the 2, you can't get there. All right, and then for this one, it's also 1 because you can only move right. For this one, there's only 1. But now let's fill in again some of the inner ones. So how many ways are there to get to this point right here?
Two.
Why is that?
You can move from the 2 to that point and from the 1 to that point.
Okay, so there's 2 ways. There's one way to get from this point to here and one way to get from this point to here. But remember, there was 2 ways to get from A to this point of 2. There's 2 ways to get from this point to this point. So what that means is there's 2 ways to get from this point to this point that go through this point. And then there's 1 way to go from this point to this point that go through this point.
So 3
And
ways.
so the total is 3, yeah. And then what about this one?
3 as well.
Yeah. Let's keep filling this in. Hopefully we'll see a pattern soon if you don't already see one. So there's 1 way to get to this point over here, 1 way to get to this point over here, right? What about to this point over here?
4.
4.
Mm-hmm. And this point?
4 as well.
Yep. Then what about this point?
6.
6.
6.
Yeah, awesome. All right, we can keep going. Here it's 1. What about this one?
5.
5. What about this one?
10.
10.
And this one?
10 as well.
That's 5.
5 as well. And then, you know, if the grid were to continue here, this would be 1. Let's keep going till we get to B. So this one, what about this one?
6.
6.
6. This one,
15.
15,
20.
20,
15.
this is 15. And then what about this one?
35.
35. And then what about B, which is the initial thing we want to count here?
35.
35.
35.
35. Awesome. And then this one?
21.
21.
21.
Yeah, and so on. And we can kind of, you know, we could keep going on the grid if we wanted to. But what have you guys noticed about these numbers here? And then I'll kind of scooch back over Pascal's triangle over here. You see any similarities?
It follows the way we are using to identify Pascal's triangle. You add the numbers in the previous row to get it in pairs to give the next number and which term it belongs to.
Yeah, so you can actually see that, for example, this one is kind of equivalent to saying there's 1 way to kind of go from A to A. This row is kind of this row. These numbers are the same here. Does everyone see this? 1, 4, 6, 4, 1, and so on. Cool. So if we wanted to look at, going back to initial problem, if we wanted to think about this in a pathfinding way, we want to find an expression for the kth term on row n. What we see here is that in row n, basically anything that's along this, let's look at this diagonal, for example. Anything that's along this diagonal, so this point, this point, this point, this point, or this point, it means it's, so this is row 4 here, right? This is row 0, 1, 2, 3, 4. Anything here in the pathfinding question is going to be 4 away from point A. So basically, the distance from A to this point is 4. The distance from A to this point is 4. Here's 4. Here's 4. And here's 4. Where 4 is like, you could go 2 to the right, or 2 plus 2 down, or 3 to the right and 1 down, etc. And so let's say, again, we labeled these elements 0, 1, 2, 3, 4, 5, etc. So if we go from there, this we'll call the 0th element. This is the first element, second, third, fourth. And so how do we find an expression for the kth term of row n? So we could take an example. Let's say n is 4. And let's say we want to find an expression for the second term. That means we want to find an expression for the number of ways to get from A to this point over here. And here we know the answer is 6. As we know here, the answer is 6. But if we use a pathfinding approach to counting it, how would we count how many ways there are to get from this point A to this point?
It would be a combination of n choose 2.
Right. So in this case, it would be 4 choose 2, because there's basically we need to go 4 blocks, and 2 of them need to go right, and then 2 of them need to go down. So this would be 6. So can we generalize this? Say we care about the nth row and the kth term of Pascal's
Equal
triangle.
N choose K.
Yeah, so this would just be n choose k. So now if we bring this back to, let's say we kind of like rotate and look back at Pascal's triangle, then another way we could write Pascal's triangle is actually we could say, all right, let's call the 0th term just 0 choose 0, and this is just 1. Then the next line could be 1 choose 0, 1 choose 1. The next line could be 2 choose 0, 2 choose 1, 2 choose 2. Then it could be 3 choose 0, 3 choose 1, 3 choose 2, 3 choose 3, and so on. And this is exactly equivalent to Pascal's triangle. So for example, this is 1, 1, this is 1, 2, 1. This is 1, 3, 3, 1, etc. So basically, that solves number 2, which is find an expression for the kth term on row n. And then the last piece of this that's kind of interesting is find the sum of the n plus 1 numbers on row n of Pascal's triangle. So there's a couple ways we could do this. We could first just look at our example here, and let's sum the numbers and see what we get. So if we sum the first row, we just get 1. If we sum the second row, we get 1 plus 1, which is 2. If we sum the first row, if we sum the second row, we get 1 plus 2 plus 1. That gives us 4. If we sum the third row, we get 1 plus 3 plus 3 plus 1, which is 8. If we sum the fourth row, what do we get?
16.
16. And if we sum the fifth row, what do we get?
32.
Yeah.
It's powers of 2.
Yeah, so we see this as powers of 2. This is 2 to the 0, 2 to the 1, 2 to the 2, 2 to the 3, 2 to the 4, 2 to the 5. So more generally, we could kind of speculate that for row n, so for row n, we have n choose 0, n choose 1, n choose n. Here we have the sum is 1, 2, 4, 8. We could say the sum here is 2 to the n. Does everyone see why that's true? Anyone can explain why that's true?
Because the number in the bracket is what 2 is squared to, so you get 2 is the power n if it's the n number.
Okay, let me try to rephrase. I think I see what you're saying. There's a couple of different explanations. So the first one is you could go back to our path finding, our path counting thing, and we could see that for each row, we actually want to count the total number of paths that are distance n away from A. And so if we want to count that, for example, say n is 4, then we could look at, okay, there's basically 4 blocks that A has to travel. And for each of those blocks, we could pick right or down. So that gives you 2 times 2 times 2 times 2, which is 2 to the 4. And more generally for n, basically we're counting the number of total ways that A can travel n blocks. And for each block, A could go right or down. So that's 2 to the n. That's one way to do it. Another way is to map this back to what we learned about subsets. So remember, we actually derived this earlier. I'll scroll back to that, which was here. We actually counted the number of subsets and we found this identity. And so we hopefully see that this is actually just another way to think about number of subsets. So in the pathfinding way, you basically want to say like, okay, how many subsets or how many like paths can I go of length n that have 0 downs, or how many paths of length n have 1 down, how many have 2 downs, all the way to how many just go n down. And so we've kind of re-derived the same identity here, back here, with the paths in Pascal's triangle. It's just the same identity. Any questions?
No, please.
Cool. Well, I think this is pretty cool. Hopefully there's some interesting identities that you've learned here. All right. So I think we have time. We'll cover one more type of counting problem with combinations. So here's another type of question that you might see that maybe surprisingly we can also solve with counting and combinations. So in basically the following series of equations, we want to count the number of solutions where the variables are restricted to non-negative integers. So non-negative integers means it has to be 0 or greater. It can't be a negative integer. And so we'll kind of use that as a clue of like, if we see non-negative integers, then we might want to use that to count something. Whereas if you have negative integers, that's not really, doesn't necessarily map to something you might count, because you don't really count negative things as much. Although we could potentially transform negative ones to non-zero ones. So we'll see some examples of transformations in the future. But let's first look at this example. So the question here is, how many solutions in non-negative integers are there to each of the following equations? And so let's just work through some of these before we think about how to generalize. So how many non-negative solutions are there to a plus b plus c equals 0? just to get started?
1.
Yeah, so there's just one, which is if I write the solution as A, comma B, comma C, basically they all have to be 0. So just one. What about B, which is A plus B plus C equals 1?
3.
3.
3, yeah. So basically you could have 1, 0, 0, or 0, 1, 0, or 0, 0, 1. So this gives us 3. All right. What about A plus B plus?
3 as well.
No, 6.
Yeah, that's right. So it's 6. And basically we can start to think about like, how do we actually write these down? So instead of trying to squeeze it here, I'm going to show you how a different way we can count them. So I guess an aside before I get there, just because it's written here, where we have equations where each variable is limited to the set of integers or a subset of integers, we call these Diophantine equations. So it's just a name for the equation. And it's kind of a common number theory topic. And for these, because all of the terms are linear, because we don't have anything like x squared or x cubed, we call it a linear Diophantine equation. So just FYI, if you see that term, there's a lot of like cool things about Diophantine equations, and kind of in more advanced math. But going back to the original question, so we talked about how for A, the answer is 1. There's only one ordered triple, which is 0, 0, 0. Here we wrote out all the possible solutions, which was just 1, 0, 0, 0, 1, 0, or 0, 0, 1. But we might look for a different way to represent it to see if we could draw it out, and this will be useful as we consider n, larger n. So here, maybe we could draw out like, we basically have to sum everything to 1, so let's have a star represent that 1, and then A, B, and C. So in this case, we could put the star in any of the columns, A, B, or C. And so if the star is in 1, that's sort of the solution 1, comma 0, comma 0. This is the solution 0, 1, 0. This is the solution 0, 0, 1. So this gives us a total of 3 solutions. That's what we just said. For C, we could think about how to draw out the solutions. So it's a little bit harder because now we have 2 stars. But basically, remember this is A plus B plus C equals 2. So basically we have 2 things we want to see like between A, B, and C where we can distribute them. So if we draw out stars here, we can basically say, okay, we could put both stars in column A. That gives us the solution 2, 0, 0. Or we can put 1 star in column A, 1 star in column B. That would give us the solution 1, 1, 0. This next one gives us 1, 0, 1, 0, 2, 0, 0, 1, 1, 0, 0, 2. And so this gives us 6 solutions. Any questions so far?
No, please.
All right. So for D, the question was A plus B plus C equals 3. So far we have these diagrams. We're just kind of listing them all out. And we see, hopefully you see that as n grows larger, it's going to be harder and harder to count all of these and make sure that we're not overcounting or missing something, or double counting or missing something. So we want to see like, how can we generalize these diagrams to help? And so here's one for A plus B plus C equals 3. So if we draw all the stars, these are all the solutions. I'll kind of write them out just so we can be clear. So here we have 3, 0, 0, 2, 1, 0, 2, 0, 1, 1, 2, 0, 1, 1, 1, 1, 0, 2, 0, 3, 0, 0, 2, 1, 0, 1, 2, and 0, 0, 3. So if we count all of these, we see there's 10 solutions. But it's definitely getting harder to write them out, right? So let's think about how we can turn these diagrams into kind of more of a pattern and kind of make that into a combinations problem. So basically, we can think about how the variables are important. So we want to basically distinguish like A, B, and C, and the order of A, B, and C matters. So what I mean by that is 3, 0, 0 is a distinct solution from something like 0, 3, 0. And so instead of having column labels, we could kind of transform these solutions into by basically drawing a bar here. I didn't do too much, but we can transform these solutions into, say, star, 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 and then we have a bar and a bar. Or this one is star, star, and then we have a bar here, and then a star, and then a bar. And so here we've actually labeled all of them. Let me zoom out a little. So for example, here, star, star for A, then we have nothing for B, then a star. We could represent this as star, star, bar, bar, star. So basically what we're doing here is we're representing kind of these barriers here between the variables as just a symbol like a bar. So we're turning just these solutions into a sequence of stars that represent the ones that we're summing and bars that represent the variables. So does everyone see how each of these solutions maps to one of these sequences? So for example, here's another one. This would map to star, bar, bar, star, bar. Sorry, star, bar, star, star, bar, star.
Yes.
So there's a couple of different observations here that are key to solving this problem. So, and we have them written down here. So the first one is right here. So for every ordered triplet of non-negative integers that satisfied A plus B plus C equals 3, there is a row or a sequence of exactly 5 symbols, 3 of which are stars and 2 of which are bars. So for example, if we have, you know, A equals 2, B equals 0, C equals 1, then that maps directly to star, star, bar, bar, star. Because basically this you could think of as the A column, this is the B column, this is the C column. And so this gives us 2, 0, 1. The second observation is for every possible sequence of 5 symbols where there are 3 stars and 2 bars, there is an ordered triplet of non-negative integers that satisfies A plus B plus C equals 3. So for example, if I have just any sequence of 3 stars and 2 bars, so let's say I have, you know, star, bar, star, star, bar, then that will map to one solution of this equation. So here, again, A column, B column, C column, this maps to the solution A equals 1, B equals 2, C equals 0. That satisfies A plus B plus C equals 3. So if both of these are true, then what we found here is what we call a one-to-one correspondence. between the solutions of a plus b plus c equals 3 and the sequence of symbols of 3 stars and 2 bars. And so with a one-to-one correspondence, that means we're actually counting the same number of things. So once we've established this one-to-one correspondence, that means we can count the number of solutions of a plus b plus c equals 3 by counting the number of arrangements of 3 stars and 2 bars. And we already know how to do that. That's like something we talked about just previously on combinations. It's kind of the same as saying, I need to walk 5 blocks and 2 of them are south and 3 are east. So here, if we want to look at the number of arrangements of 3 of one symbol and 2 of another, then we know that answer is just 5 choose 2, which is 5 factorial times 3 factorial times 2 factorial, which is 10. So let's look at the next one, which is a plus b plus c equals 4. So how do we count how many solutions are to this, this problem? Any ideas?
There'll be 15 solutions. What I've noticed is that they are triangular numbers, so it's 1, 3, 6, 10, and 15, so it will be definitely 15.
That's right. Let's see if we can use this bars and stars argument. So basically we have 4 objects and so basically we have 4 stars. And there's 3 variables, so we need 2 bars or 2 dividers. And so each sequence of 4 stars and 3 bars maps directly to one solution. And also each solution we can represent as 4 stars and 2 bars. So if we use the stars and bars approach, then the number of ways we can arrange 4 stars and 2 bars is just 6 choose 2, which is 15. And that is also the number of solutions to this equation. One thing to note that was called out in these lecture notes is the number of bars is 1 less than the number of variables. And the reason for that is we kind of, if you wanted to list out all the solutions, basically we need to put a divider between the solutions. And so there's 2 dividers that we put in for every, let's say, solution. And so this gives us 4 stars and 2 bars.
So if we always get A plus B plus C, it means there's always going to be 2 bars.
Yeah, that's right. That's right.
Miss Wendy, I was thinking about another way in which you could solve this problem in my head. I was wondering if you could do it like this. You could talk about, at least for the smaller numbers, you could look at the different positions in which the variables can be placed. Like you can fill 1, you can fill 2 of them, you can fill 3 of them, and then you can arrange them in this many factorial ways. And then if you repeat any, you just divide and you sum the total.
I'm not sure I understand. Can you give an example for this a plus b plus c equals 4?
Like, yeah, for that one, you could say that you could start with using only one number and not using the other variables. And then you can move on to using 2 of them and leaving 1 variable. And then you can use all 3 of them. And you can organize each of these different organizations through factorial ways. A can be 4, B can be 4, C can be 4, and and since we say we're repeating the zero, which is the B and C, we divide by 2, which tells us that it can only arrange the first one 3 ways, and then we sum with the others the same way.
So I think what you're saying is, let's look at this example, like A plus B plus C. You can basically like organize your thinking into different cases. And so here you can say, okay, for A could be 3, or A could be 2 and B could be 1, or A could be 2 and C could be 1. Is that what you're saying?
Yeah, yeah. And then based on, you can organize their positions into different ways. And we have 3 variables, so 3 factorial ways for each of the different cases. And then if any variable repeats or any number repeats, you just divide by the number of times it repeats to get your answer.
Yeah, I think you can definitely count this in different ways. It sounds like for that one, you would have to be a lot more careful about listing out all the solutions and kind of making sure you're correcting for the repeated numbers and stuff like that. And so you can certainly list them all out and count that way, but it's going to be a lot faster and less error prone if you think about it in terms of this like stars and bars approach. So here we could spend time listing out all of this in this table, and we could see that the answer is 10. But it's going to be a lot harder if I say, okay, what if there's like 6 variables and we want to sum to 100? Whereas with stars and bars, this is a way that we could generalize and solve it much faster.
Okay, thank you.
Yeah. So let's move on to kind of a more general formula here for this problem. So for part F, we want to say how many solutions are there to A plus B plus C equals N. And so here we can say we want to arrange N stars and 3 minus 1, which is 2 bars, if there's 3 variables. And so that means we want to do N plus this many bars, and we want to choose N of them to be stars, or we could say we want to choose 2 of them to be bars. They're equivalent. And so in this case, the answer is N plus 2, choose 2. And so to kind of illustrate how this problem can help you, or this approach can help you solve much more complicated problems where it's harder to list out all the solutions, we can try to generalize further. So say we want to find the number of solutions to this general Diophantine equation, where instead of having just 3 variables, we have k variables, and we sum to n. So let's see if we can derive a formula for this. So if we use the same approach, basically we have n stars, and then we have k minus 1 bars. Does everyone see why that would be the case?
Yes, please.
Cool. So if we use that same approach, that means we have n plus k minus 1 total things, of which we want to choose n of them to be stars, or n plus k minus 1 of them, of which we want to choose k minus 1 of them to be bars. And this is actually an equivalent quantity. And so what this is saying is the number of non-negative solutions to this equation is just this expression. So there's other ways we can think about this. And if you read this in other books, you might, instead of seeing stars and bars, maybe you see like balls and bins, or marbles and urns. So let's think about something else. So let's say we want to say how many ways are there to place n distinguishable balls into k distinguishable urns. This should say indistinguishable balls. So we have n balls that are the same, and then k urns that are different. So let's say we have like, you know, one urn B, A, one urn B, one urn C, and we have n balls that all are the same. This is important. How many ways are there to do that? Do you all see why that's the same as the number of solutions to this equation? Or in this case, it would be A plus B plus C equals 4. So in this drawing, for example, the number of balls I put in bin A is just the value for A. Number I put in bin B is just the value for B, and the number I put in bin C is the value for C. So basically we've derived like 3 equivalent problems here. So the first one is, you know, how many solutions are there to the equation A1 plus A2 all the way to AK equals n, where A1 through AK are non-negative integers. The second is, how many ways can I sort of order k minus 1 bars and n stars in a sequence. The third one here is, how many ways can I put n indistinguishable balls into k distinguishable bins. So let's try let's try some other problems because not every problem follows the same pattern. And so one of the things that I think we want to develop here is to find a way to relate different problems back to similar ones that we already know how to solve, so we can apply the methods we already know to solve more types of problems. So let's see what else we can solve with this. Here's a question. How many different 3-digit numbers exist where the sum of the digits is equal to 9? So any ideas on how we can do this?
You could list you could list all the numbers that sum up to 9. 3 numbers that sum up to 9.
Yeah, that's possible. We could list them all out. But as we found earlier, that's actually a lot to list out, right? Are there any other ways we could do it? It's definitely possible to list them all out.
We can think of it as A plus B plus C equals 9 and use the stars and bins to find out how many numbers we can organize that way. But then there's also the fact that some of them will start with 0, so we'd have to find a way to remove the one that starts with 0 from our counting.
Right, yeah. So let's say we have A, B, C is our 3-digit number, and we know A plus B plus C equals 9. And then we know that A has to be greater than or equal to 1, B has to be greater than or equal to 0, and C has to be greater than or equal to 0, right?
Yes.
Cool. So we know how to solve the problem if A could be 0, but here we need to figure out how to correct for the fact that if we just look at how many solutions there are to A plus B plus C equals 9, that we're going to count a bunch of solutions where A is 0. So one way we could think about this is, since we know A has to be at least 1, we could define some other variable. Let's say, let's call it A prime. And let's just define A prime to be A minus 1. So this means that A prime is just greater than or equal to 0. And so if we plug this in, here, let me say A prime equals, yeah. So say A equals a prime plus 1, and also a prime is greater than or equal to 0. So if we plug this in here, then this equation becomes a prime plus 1 plus b plus c equals 9, which we can write as a prime plus b plus c equals 8. And now we've transformed this into an equation we know how to count the number of solutions to, because we know a prime is greater than or equal to 0, b prime is greater than or equal to 0, c prime is greater than or equal to 0, and they're all integers, or they're all non-negative integers. So how do we count the number of solutions to this?
So this one we can now sum the stars. So there will be 2 bars and then 8 stars. So 10 choose 8 or 10 choose 2, and that will give us the total number with zeros included. And then we can say that that's the same for 9 because we had a prime.
Yep, that's right. So basically this will give us 10 times 9 over 2, which is 45. This is the number of solutions to a prime plus b plus c equals 0. A prime plus b plus c equals 8. And then for any solution here, we can transform it back to our 3-digit number by adding 1 to a. And then that will give us a 3-digit number. The other thing I want to note here is that one reason this works is because the sum is 8, or here that the sum is 9. If the sum were greater than that, then we would also have to make sure that we're not counting digits that are, say, 10 or above. But here, because none of the numbers can be greater than 9, that this still works. So that gives us the total is 45.
Could we say that in any situation where one of the variables is restricted, we would subtract 1 from the actual total we're supposed to get and work it out from there? Can we see that?
I don't know that that's exactly true. You basically have to look at like what the restriction is. So let's look at another example in the last few minutes. We'll skip this one. Or maybe we could do this one. This one's a little more straightforward. So this one says, let's do this one. The sum of the last 4 digits of Marion's phone number is 30. How many such 4-digit sequences are there? So here we also have a similar restriction. So we have 4 digits here, A, B, C, D, and we know A plus B plus C equals 30. And then the restrictions we have here are that A, B, C, and D are digits, so they have to be between 0 and 9. So any ideas on how we can do this one? This one's a little trickier.
We can do the 30 plus the number of bars, 33, so it will be 33 total, and then it would be 33 choose 3 to get the total number of solutions.
So that would be true if we didn't have the restriction that A, B, C, and D have to be less than or equal to 9. So if you did that way, you'd be counting things like A equals 30, B equals 0, C equals 0, D equals 0.
So could we subtract 1 from the total like what we did at the previous problem?
So you could do something similar, but it's not exactly the same. So in the previous problem, the reason we subtracted 1 was because there was just one number, which was a, that had a restriction where it could be greater than or equal to 1. So we transformed that into something that was greater than or equal to 0. So in this case, we have to kind of do some creative thinking to think about how to transform this back into a type of problem that we know how to solve. So one thing that I'll note here is because all these numbers are less than or equal to 9, that means the maximum sum of any four-digit sequence is 36, which is if all of them were 9s. So one thing we could think about here is we know the sum is 30 and the maximum sum is 36. So we need to somehow subtract 6, basically some numbers from here to make 6. So for example, let's transform this. Instead of saying A, B, C, and D, I want to actually have 9 minus A prime, 9 minus B prime, 9 minus C prime, 9 minus D prime. And we want these to sum up to 30. So 9 minus A prime plus 9 minus B prime plus 9 minus C prime plus 9 minus D prime equals 30. If we rearrange, we basically get, or let's first sum. So we get 36 minus A prime plus B prime plus C prime plus D prime equals 30. If we rearrange, we get A prime plus B prime plus C prime plus D prime equals 6. And we have the same restrictions here where 9 minus A prime, for example, is greater than or equal to 0, less than or equal to 9, which means that A prime is greater than or equal to 0 and less than or equal to 9. Okay. So we've transformed this problem now into something we know how to solve here. And because A prime, B prime, C prime, D prime, if we just assume that they're positive, right, then we know how to solve this. And then furthermore, the sum is 6. So if the sum is 6, then none of them can be greater than 9. So now we can count how many ways are there, how many sequences are there, A prime, B prime, C prime, D prime, that are non-negative integers that sum to 6. So how do we apply stars and bars to count that?
The bars will be 3. So you add the 3 to the total number, which is 6, and to give you 9.
Yeah, so here we have 3 bars and 6 stars. So the total number of solutions to this is going to be 9, choose 3. Which we can write out. This is 9 times 8 times 7 over 6, or just say 3 times 2. So we can cancel this 3 times 4. So this gives us 12 times 7, which is 84. So the key here is the fact that the number of solutions to A prime, B prime, C prime, D prime equals 6 with these restrictions is the same as the number of solutions to this with these restrictions. And so once we see that, then we can just count the number of solutions to the A prime, B prime, C prime, D prime equals 6 solution, and that will give us 84 for the answer to the problem. Any questions?
No.
All right. So I posted the handout related to this this lecture in Piazza. I'll also upload the annotated version here. And then for homework, there's a lot more examples here that I would suggest that you all go through. And there's also solutions included in this PDF. All right. So thanks everyone for coming. I will see you all on Friday for office hours. And if you have any questions in the meantime, as you're going through the material, please just post on Piazza.
Thank you, Miss Wendy.
See you all
Thank
later.
you.
Bye.
Thank you. Bye.
Okay, thank you. Bye. See you.
Bye.
Bye.